Symmetry is an important geometric concept, and it shows up in our study of functions. And so I'm going to introduce it here. And there are two major kinds of symmetry. Actually, off the top of my head, I'm not sure if there's anything else, but geometric symmetry tends to either be line symmetry or rotational symmetry. And the rotational symmetry we're interested in is a special one called point symmetry. So we're going to study line symmetry and point symmetry. And it turns out that you can recognize these features analytically through the algebra of a function. And so it's possible to determine the symmetry through the algebra of a function without looking at its graph. But anyway, let's talk about these. And this topic will be about the line symmetry. So I didn't trust myself to freehand one of these very well, but I drew a line L, and here's a rectangle. And then I tried to imagine, well, what would this rectangle look like if I were to reflect it around the line, across the line. So by reflection, I mean that we're spinning it around the line to form the mirror image. And this looks reasonable to me. It's close enough. It's not a perfect drawing, but that's the idea of line symmetry. Now, how would you begin to define this? Well, let's take some landmark points here. Like, for example, this corner that's nearest to the line, if I draw a perpendicular segment to the line, and then I extend this segment over to here, I arrive at this point. So these 2 points have line symmetry because you can connect them with a line segment that is perpendicular to the line of symmetry, and these 2 segments are equal. In other words, the line crosses at the midpoint of this segment. Same over here. If I connect this dot and this dot, those corners, then the segment forms a perpendicular and the line is at the midpoint of that segment. So you can go through and do that, and that's a way, we could turn that into a mathematical language and interpret it, particularly in terms of algebra. It's possible to do that. So in order to try to describe this in terms of algebra, we have to find a language to describe it and then interpret it into the language of algebra. So that is possible. So that is an example of, let me write the term out, line symmetry. Symmetry has 2 M's, by the way. Line symmetry. And I'm going to give you some examples of functions which have line symmetry to them. So let me erase the board here and put some up. My first example of a line symmetric function is y equals x squared. And this forms a shape called a parabola. You're going to become very familiar with that function by the time we're done with this course. And it touches at the origin and goes back up. So it dips down, touches at the origin, and goes back up. The line it's symmetric to is actually the y-axis in this case. And that makes it extra special. Because when a function is symmetric to the y-axis, we call that an even function. So that's something we're going to explore later on in a different section, even and odd functions. But it's a special property that's kind of significant. All right, so you can imagine that the right half of this parabola can be flopped over to the left half and back and forth. So this symmetry is a vertical line symmetry. And now let me give you another one that has a vertical symmetry, line symmetry to it. Let's look at the cosine function. So cosine is abbreviated COS, and we don't study cosine in this course because it's a trigonometric function, but I can still show you its picture, and it's a wave pattern which goes up and down, and extends forever in all directions. And so this wave pattern, it turns out that this point would be 2 pi, and this point would be pi. You could substitute 180 degrees and 360 degrees. So if you take trigonometry, you find out that we don't just measure angles in degrees, we have other ways to measure angles. And this particular form of measurement is called the radian. All right, you don't have to worry about that, but now, of course, it does top out at 1. So this cosine function, which again extends to infinity in both directions, if you take the right half and flip it around, you'll get the left half. And so it is symmetric to the y-axis. And now it's also symmetric to this vertical line. And so I took the right half and flipped it around, I would get the left half again. So this has a lot of different, actually has infinitely many different line symmetries to vertical lines. But of course the most interesting symmetry for line symmetry is the y-axis, and that too makes it an even function. So now, is it possible for a function to be symmetric about the x-axis? You think about that in a minute. You know, what does it mean to be a function? If it's symmetric about the x-axis, that means that if you took the top half and flipped it over, you would get the bottom half. And so if you had a top half and a matching bottom half, it would be symmetric to the x-axis, but it would not be a function, would it? Because if there's a top and a bottom half wrapping around the x-axis, then you've got at least 2 points here that a vertical line would hit. It would not pass the vertical line test. So functions cannot have symmetry to a horizontal line or the x-axis, but certainly not to a horizontal line. All right. Well, is it possible to be symmetric to other lines? That's a good question. I have to think about that, and maybe I'll figure one out, but not in time for this video. So I have a feeling that functions can only have line symmetry around vertical lines. So okay, well that's what I had to say about the line symmetry, and let's go on to the point symmetry.